All right, this is the lesson on 2.3, free fall. So if I drop the textbook and a piece of paper at the same height, would they fall at the same rate? Right, so if you drop them side by side, you realize, well, the textbook or whatever object you're dropping is falling at a faster rate. It would reach the ground at a faster time. But what about if you place the piece of paper on top of the textbook? Now, if you've never seen the in-class demos and you never watched the other first video, then, well, try it yourself. And it doesn't have to be a textbook, it can be like a notebook or a folder. Just make sure that the piece of paper is directly on top of the folder or the book, and make sure it covers most of the area of the paper. And when you're dropping this paper that's on top of the textbook or book, make sure you're not holding the paper on top. Make sure you're not clamping down on it with your thumb. And if you do it, you'll realize that, well, my textbook and my piece of paper, they both fall down at the same rate, which is something you wouldn't expect, right? You wouldn't expect that to happen. But why does that happen? Well, that happens because of air resistance, right? Because air resistance causes objects to slow down, right? And if you were in a vacuum, right? If you were in a chamber with no air, then you would see that both objects fall down at the same exact rate, right? So the paper, because it's not experiencing it's not experiencing air resistance, right? There are no air atoms hitting the paper. It's not being slowed down. So assuming that there is no air resistance, so that there is no atmosphere, we can say that all objects drop at the same exact rate, at a rate of negative 9.8 meters per second squared. That is my acceleration due to gravity. The acceleration due to gravity is negative because, well, you're dropping downward. Now, from our definition of acceleration, our acceleration due to gravity is negative 9.8 meters per second squared, right? But how is the velocity of a falling object affected each second? Now, if you take a look at the right-hand side, if you take a look at the right-hand image right here, you'll see that, well, my velocity is first 0. But since my acceleration is negative 9.8, you realize that at the next second, my velocity is increasing by negative 9.8 meters per second, right? And then the next second, you see that my velocity increases to negative 19.6. And the next second, my velocity increases to negative 29.4. So there's a pattern here, right? There's a pattern. And the pattern is that, well, I'm increasing by negative 9.8 each time. Each second, my velocity is increasing by negative 9.8 meters per second, which is coincidentally what my acceleration is, right? My acceleration is the change in velocity over time. Well, how much is it changing by? It's changing by negative 9 meters per second each second. Which brings us to our next slide. Because if you take a look at the unit, right, the unit for meters per second the unit for acceleration is meters per second squared, which is really important here because your acceleration tells you how many meters per second your velocity changes per second. That's why it's squared, right? That's why it's second squared, right? If you think about it, right? So my initial velocity, let's say my initial velocity is 0. My initial velocity is 0. And my acceleration is negative 9.8 meters per second squared. That means that my velocity is changing, right? My velocity is changing by negative 9.8 meters per second every second. And if you were to do meters per second over seconds, right? If you were to do meters per second over a second, you would get meters per second squared. And that's where the unit comes from, right? That's where the unit comes from. Your acceleration is the change in velocity over time. Well, it tells you how many meters per second your velocity changes by. So if you say that, let's look at the bottom here, right? If you say that your acceleration is 5 meters per second squared, then your velocity is changing by 5 meters per second every second. Your acceleration is the change in velocity over time. And on the bottom here, if I say that my acceleration is negative 7 meters per second squared, then my velocity is changing by negative 7 meters per second every second. All right. All right, so a ball is dropped from a rooftop by a 40-40. So let's do some practice problems now, right? So now that we've got the concepts out of the way, you won't be necessarily tested on the concepts. It's just nice to know what these concepts mean, right? What acceleration truly is. So let's say a ball is dropped from a rooftop of a 44.1 meter building. A ball is dropped. What is the time it takes to get to the ground? Now, there are a lot of pieces of information you can gather from this problem. Two of these are assumptions you can make. When you say a ball is dropped, right, you're dropping a ball, you can say that, well, if you're letting go of a ball, you can say that, well, my initial velocity here is 0, right? I'm letting go of this object. I'm letting go of this object and say my initial velocity here is 0. Ball is dropped from a rooftop of a 44.1 meter building. Well, you have to think about it this way, right? If you're dropping from a 44.1 meter building, we say that essentially where we start is 0 and we end up 44.1 meters below 0, right? Because anything below 0 is going to be negative. So my displacement here, right? My displacement here would be negative 44.1 meters. I'm 44.1 meters away from where I started, below 0. I started at 0 and I landed 40.1 meters below it. So my displacement here is going to be negative. We can come up with another assumption here, and our assumption here is that, well, my acceleration due to gravity is negative 9.8 meters per second squared. Right? It's negative because my direction is downward, right? My force through gravity pulls my object downward, and that means that my acceleration here is negative. The question says, well, what is the time it takes to get to the ground? So what is t? And so which formula do I use? Which kinematic formula do I use? I use this one. So d is negative 44.1, vi is 0, negative 9.8, t squared. And we can use this formula because it has all the variables we need, right? It has everything. And if you use the other ones, you wouldn't find all the variables you need. So you have this. So negative 4.9 t squared. Right, so 1/2 times negative 9.8 gives you negative 4.9. We want the t by itself. The square is attached to the t directly, right? So that comes before, that goes after the 4.9. So the 4.9 is furthest away from this t, right? Because the square is closer. So we're going to get rid of this negative 4.9 first. Now this 4.9 is attached to that t squared by multiplication. So we have to do the opposite. We have to divide, right? We have to divide by negative 4.9. And then we get, let me see, 4.9. I think we get 9. Let me just double check real quick. We get 9, right? So we get 9 here. We get 9 t squared, and then we get rid of the square by doing this. So 3 seconds gives us t. All right, so that's 3a. 3b. An object dropped from rest. Right, so an object dropped from rest, you can already tell that if you're dropping something from rest, well, you can say that my initial velocity is 0. It hits the ground with a speed of 20 meters per second, right? So it hits the ground with a speed of 20 meters per second. So my final velocity is going to be 20 meters per second. But since your velocity is going downward, you have to realize here that your velocity is negative, right? Your object is going downward, so your velocity here is negative. Your final velocity, rather. And you can basically come up with the assumption here that, well, since we are dropping, we can say that, well, my acceleration due to gravity is negative 9.8 meters per second squared. And then we are looking for distance traveled, so we'll use d. So the only formula we can use here is this. So negative 20 squared, 0 squared, plus 2, negative 9.8, d. All right, so now we have this. And so this is this multiplication, we have to divide. And we get something like 20.4. So we get something around negative 20.4 meters. Now the reason it's negative is because this d right here means displacement. Since we are working with vectors, and since displacement is a vector, that's going to be negative 20. That's going to be negative, right? Because your displacement is negative. You went down. Your ending location is below 0. But the question wants distance, and distance is just a scalar version. So our answer is just going to be positive, right? So scalar versions don't really care about direction. They really just care about the number. So our answer is 20.4. So our question here, 3C. So 3C says a ball is dropped again. Right, so we can say that, well, my initial velocity here is 0 on another planet. And since we're on another planet, we're no longer on Earth, well, we can't really assume that my acceleration due to gravity is negative 9.8 meters per second squared, because we're on a different planet with different gravity. And so a ball dropped on another planet hits the ground with a speed of 48 meters per second, right? And so since we know that this is a velocity unit and you're going from one speed to another, it hits with a speed. So we can say that, well, my final velocity is going to be negative 48.3 for negative 48 meters per second. And the reason why it's negative is because, again, your object is going downward, right? So since it's going downward, we say that it is negative. Now that the ball took 8 seconds, right? The ball took 8 seconds, so that's your time to hit the ground. What is your acceleration due to gravity, right? So what is your acceleration here? And so the only form we can use is this one, right? So negative 48, vi 0, a is a, and t is 8, negative 48, 8a, divided by 8, negative 6 meters per second squared gives us a. All right, and that is our answer. And then you can watch the video, the summarization video yourself. All right, cool.